Okay, so our AP style problem is going to start out by saying write the first three non-zero terms and the general term of the Taylor series for f of x equals cosine of x plus x times the sine of x centered about x equals 0. So this is a Maclaurin series. Since we're centered at x equals 0, I haven't really done much that's centered around other numbers. We'll save that for another day. But here's the first thing I'm going to do. Similar to yesterday, I am going to break this down into parts. I'm going to take the Maclaurin series for the sine of x, and I'm going to multiply it by x. You guys can see it there. X squared minus x to the fourth over 3 factorial plus x to the sixth over 5 factorial minus x to the eighth over 7 factorial. And in fact, if I want to write a more generalized form for this in sigma notation, I can take my sigma notation for the sine of x, the Maclaurin series in sigma notation for the sine of x, and I just have to multiply it by x, which is reflected right there. Instead of having x to the 2n plus 1, I have x to the 2n plus 2 because I've multiplied by an x to the first. Okay, then I can also take my Maclaurin series for the cosine of x, and that's 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and hopefully we're starting to memorize these. And in sigma notation, I've done something a little different here. I took the sigma notation that you guys are used to, I'm going to write it up at the top of the screen, and I kind of tweaked it a little bit for this particular problem. We need to be willing to kind of tweak our sigma notations to make them do what we need them to do when we're working on AP problems. So the one that you're used to is negative 1 to the n times x to the 2n over 2n quantity factorial. And if you recall, what that's going to do is it's going to go 1 minus x squared over 2 factorial, etc. I just said that. But what I'm going to do is I'll write 1, the first term in it, and then I continue my series in sigma notation after that. And there that is. So really what I did is I wrote the first term, and then I kind of re-indexed or rewrote my sigma notation. Let's see, if I start at 0 and go to infinity, then if I'm starting at the second term in my Maclaurin series, I'm not starting at n, but I'm starting at n plus 1. X to the 2 times, instead of n, it's n plus 1, over quantity 2, instead of n, it's n plus 1. And then when you simplify all of that, when you distribute those 2's, essentially, gets you to that sigma notation. Now you might be wondering why the heck I did that. The main reason is now if you compare my sigma notation for x sine of x and my sigma notation for the cosine of x, these are both x to the power 2n plus 2, and it's going to make it a lot easier then to add these together. So let's go to the next slide. If I take the cosine of x plus x sine of x, first of all, it's kind of easy to do away from that sigma notation. It's kind of easy to do this because we're just going to go term by term. If I do x squared minus x squared over 2 factorial, that's just x squared over 2. If I follow this term by term, if I do negative x to the fourth over 3 factorial plus x to the fourth over 4 factorial, that's going to be minus x to the fourth over 8. And then, you know, going to kind of continue this on. If I do x to the sixth over 5 factorial minus x to the sixth over 6 factorial, that's going to be x to the sixth over 144. And then for the sigma notations, if you add these two sigma notations together, it'll give us this third one, which I'm highlighting right now. Okay, so we've completed our task. It says write the first 3 non-zero terms and a general term. In fact, I wrote 4 non-zero terms at the beginning, just because it'll be a little useful later. And then I also wrote a sigma notation. Now you might be wondering where the heck this sigma notation came from, because I kind of just had it appear on the screen and I didn't show how to get it. On the next slide, I will show you how to go from the sigma notations that I'm highlighting now and how I can add those together to get this third one. So let's go ahead and go to the next slide. Oh, by the way, this converges for all real numbers, all x's in the set of real numbers. The reason that works is cosine converges for all real numbers, and x sine of x is going to converge for all real numbers. So this whole thing is going to converge. So, okay, write the first three non-zero terms. Same thing again. This is part A. All I'm going to do is I'm going to show you how we could take those two sigma notations from the first slide and add them together and get that final answer that we had on the previous slide. So this is really all about getting our general term. I'm just going to show you the kind of algebra behind it. So here's the one that we had from x times the sine of x, or sorry, the one that we had from x times the sine of x. This is the one that we had for the cosine of x. And if I take those and try to add them together, well, first of all, what I can do, let me switch highlighters here. If you take a look at this quantity, negative 1 to the n plus 1, what I can do is I could take one of those negative 1s, make this a minus sign, and then my power just becomes an n. So that's where that comes from. And then, in addition, if you look at the first fraction, I was originally over 2n plus 1 quantity factorial. Well, if I multiply the numerator and denominator of this first fraction by the quantity 2n plus 2, look what I can do here. I can change that into 2n plus 2 on the top and a 2n plus 2 factorial in the denominator. And the reason that this works out nicely, the reason that we want to do this, is now we have a common denominator that we can work with. So we can actually try to put all this together. So I'm going to factor out a negative 1 to the n. There it is. I'm also going to factor out an x to the 2n plus 2. There it is. And inside the parentheses, you guys can see that I'm left with a 2n plus 2 over 2n plus 2 factorial minus 1 over 2n plus 2 factorial. And when I put those guys together, well, all I have to do is the 2 minus the 1, and I get 2n plus 1 for my numerator. And there it is. Negative 1 to the n times the quantity 2n plus 1 times x to the 2n plus 2 over 2n plus 2 factorial. Now this one's a little bit over the top. I would say that all of this algebra might go a little bit beyond an AP problem, but not that much. We do have to get comfortable with the idea of taking general terms and being able to take derivatives of general terms, integrals of general terms, adding and subtracting them. Basically, we can't let these n's that pop up in the problem scare us. So let me go back to the previous slide, and we can see how these first two in the upper left-hand corner of the slide add together to make the one on the lower right of the slide. So there it is. I know this is all a mess right here, but I just want to remind you, really what we just did was we showed how to add the two sigma notations at the beginning to get this general term at the end. Okay, so that's part A, all taken care of. Let's go to part B. It says use the Taylor series for f of x about x equals 0 that we found in part A to determine whether f has a relative minimum, a relative maximum, or neither at x equals 0. We have to give a reason for our answer. This is really cool. This is a lot less tedious than part A. In fact, this is a situation where the Taylor series can make a problem a lot more efficient and really quick. So first of all, we already did the work of finding this Taylor series. And once we have the Taylor series, it actually tells us a bit about the derivatives. In fact, it tells us a lot about the derivatives of our function f of x at x equals 0. Because remember, when we defined Taylor series, we said a Taylor series, it's going to have f of 0, then it's going to have f prime of 0 times x to the first, then f double prime of 0 over 2 factorial times x squared, and that's going to follow that pattern, so on and so forth. The nth derivative evaluated at 0 divided by n factorial times x to the nth power is the general term. Well, that means that we know a lot about the derivatives at 0, including the first derivative of this function at 0. So f prime of 0 is the coefficient of x in the Taylor series for this function at x equals 0. And so actually, look at this. Between the 1 and the x squared over 2, there's a 0x hanging out in there. And so what that implies is that f prime of 0 equals 0. Well, wait a minute. When you're trying to find relative maximums and relative minimums, you're looking at a certain point. You're looking where the derivative equals 0 at that certain point. And so we have determined without a shadow of a doubt, or beyond a shadow of a doubt, that f prime is of 0 is equal to 0. So that's a critical value. Now we need to determine whether that critical value is going to lead to a maximum or a minimum, or neither, at that point. The easiest way to do that is to use the second derivative test, because I know from my Taylor series that f double prime of 0 is actually going to equal a positive number, and that's going to give us our concavity that we're looking for, concave up. But in any case, take a look right here. I have x squared over 2, and that's equal to, that coefficient is equal to f double prime of 0 over 2 factorial. So this coefficient of 1/2 is equal to f double prime of 0 over 2 factorial. That implies that f double prime of 0 equals 1, which tells us that f double prime of 0 is positive. And so since we're concave up there, that's going to imply that at 0 we have a local minimum. So kind of a neat application of Taylor series to determine whether we have a relative maximum or minimum at a point. And in this case, it's a local minimum. Okay, now we're almost done. Part C says find the first 3 non-zero terms of the Taylor series of the derivative of the function f, and also a general term. The easy way to do that is to take the answer that we already found, and here it is. This is the answer we already found in the previous part, and literally just take the derivative of it. So the derivative of 1 goes to 0. We don't need to worry about that one. The derivative of x squared over 2 is going to go to x. The derivative of x to the 4th over 8, that actually goes to x cubed over 2, or you can think about it as x cubed over 2 factorial. Likewise, the derivative of x to the 6th over 144, you could think about it as x to the 5th over 24, or a better way to look at it is x to the 5th over 4 factorial, because when you look at your general term here, when we talk about differentiating our general term, what would you do to differentiate the general term? Well, the power on x is going to be brought forward as a coefficient, and then you're going to reduce the power by 1. So let me show you that, reducing the power by 1. It's going to go from x to the 2n plus 2 to x to the 2n plus 1. And then here's the interesting thing. Look at these coefficients here. In the numerator, I'm going to have a 2n plus 2 times a 2n plus 1. Well, what happens when I have a 2n plus 2 and a 2n plus 1 in the numerator, and I'm dividing by 2n plus 2 factorial? Well, 2n plus 2 factorial, remember what 2n plus 2 factorial really is. 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, etc., etc., etc. And so if that's the case, then a 2n plus 2 is going to cancel out from the numerator and denominator, and x plus a 2n plus 1 is going to factor out, or cancel out, that is, from the numerator and denominator, and it's just going to leave a 2n factorial. There it is.